Morning, everybody. Thanks for being here. Thanks to the students for coming as well. Dick was talking about forest and different land cover. If you look at the map in your program, there's a nice colorful map of the watershed. And if you think about that map from a historic perspective, what's the primary color that you see mostly on that map right now? It's yellow, right? That's cropland. If you were to look at that map, if we were able to make that map 200 years ago, that would be mostly green. It would be mostly forest. So we've modified this watershed quite a bit. And that not only affects the surface water and hydrology and how water moves, but it also affects the groundwater. And we chose this year to kind of focus a little bit on some groundwater issues at the conference. So you'll see that there are a lot of presentations on that topic, some locally, and Kevin, who's done work all around the state, will talk about groundwater locally, but also in general, and some trends and such. So I'm proud to be able to introduce Kevin. Kevin Masarik is a groundwater education specialist with Extension. Yay, go Extension. And also at University of Wisconsin-Stevens Point. For the past 20 years, he has assisted tens of thousands of well owners in testing their water through locally organized well water testing programs. The benefits of these programs are twofold. Individual well owners are able to have a better understanding of their individual well water quality, and over time the results have helped paint a detailed picture of water quality across Wisconsin. Kevin uses information learned from his outreach and other research efforts to educate communities around the state about the effects of land use on groundwater. So please join me in welcoming Kevin Masarik.
Is the mic working? Can everybody in the back hear me okay? Thumbs up. Thanks, Jerry. Appreciate the opportunity to be here today. This is my, I believe, third time being at this conference. The last time I think was 2018, 2019, so it's a pleasure to be back. Always appreciate coming to this part of the state. We work a lot with the local communities, the counties in this region, and what I hope to do today is highlight and set up all of the great work that's going to be presented in the breakout sessions. That's really my goal. Dick said you have one goal, it's to keep everybody awake, but my second goal is to highlight and set up, get people really excited about attending the breakout and learning more, diving deeper into some of the things that I hope to cover in the short amount of time that we have here together. So as Dan mentioned, I work for Extension. Much of my work involves working with rural communities on private well drinking water quality issues. But as my bio stated, that provides an opportunity to help us learn more about what we often refer to as Wisconsin's buried treasure. It's the part of the water cycle that's the most misunderstood, but is intimately connected to all of the surface waters, all of the other recreational opportunities that we rely on water for, fundamentally are linked to groundwater. And demystifying that resource is what I do on a daily basis. And using the information we've learned over the last 20 to 50 years, we want to help paint the picture and help everybody better understand what we know about this buried treasure. So just most people in this room are very familiar with the water cycle, but I think it's really important to highlight groundwater and where it comes from. Oftentimes when we do Google searches for the water cycle, you might see pictures of mountains or glaciers and oceans. And a lot of times I think that provides the opportunity for a misconception about where our groundwater actually comes from. Groundwater is an incredibly local resource, originating as rain or snowmelt that soaks down into the ground, eventually reaching a point where all the empty spaces in the soil or all the cracks in the rock are filled with water. And that's groundwater. It's impacted by the local soils, the geology, but also the land use where that water soaks into the ground has important implications for the water that enters a lake, river, or stream, or water that might be pulled out of a private well. So anything we do on the surface, we have to be very concerned about what impact that has on water quality for those reasons. Groundwater relies heavily on geology. Aquifers are what store our water, store our groundwater, so that's important because it determines the properties of those materials, determine things like how quickly groundwater flows, how much water the aquifer can hold, how easily groundwater becomes contaminated, and the material or the makeup of those different aquifers also might impart their own impurities, and we'll talk about some of those important considerations today. Wisconsin has this layered cake geology where the oldest rocks are at the bottom. Those tend to be crystalline rocks. That's kind of the basement or the foundation of our resource. The granite does not hold or store a lot of water, so our groundwater sits in those geologic materials that are layered on top of that crystalline bedrock. They might be layers of sandstone, as is the case in most of the Red Cedar Watershed. They might be layers of dolomite, which is responsible for a lot of the issues we hear about in places like Door or Kewaunee County. There might be sands and gravels that were left behind when the glaciers receded. All of these different materials are going to impact the groundwater system as well as how easily contaminants can reach that resource. So cracks or fractures in the rock obviously are going to allow water to move much quicker. They're not going to allow as much filtering ability as, let's say, sands and gravels or sandstones. When we talk about the connection of groundwaters to surface waters, the concept of base flow index, so how much of a total stream's flow comes from groundwater or base flow versus runoff, what you'll see is that Wisconsin is pretty unique compared to its neighbors. Wisconsin and Michigan are very groundwater dominated systems. The majority of water in our rivers and streams comes from the groundwater. That's the reason why even in the middle of a drought, the smallest creeks and streams and springs are still flowing. In the middle of winter, the lakes are froze over and we're driving on them, yet that small creek is still free flowing. That's really critical for different species. So when we look at important species to our economy, things like trout fishing, those species are heavily dependent on that connection of groundwater to surface water. So if we overlay our trout streams onto those base flow dominated systems, those areas in blue are watersheds that receive more than 50% of their water from groundwater or base flow. There's a very strong correlation between those two. And again, Wisconsin is somewhat unique relative to, let's say, Minnesota or Iowa, where they have less connection oftentimes to that groundwater system. Putting us all into the context of Wisconsin, the Red Cedar River watershed is highlighted in red. Obviously part of the Mississippi River basin. Highlighting that, as all of you know, our groundwater here does not come from Canada or Lake Superior. Those are different watersheds, and those watershed boundaries not only help us understand things like how the surface water runs off over the landscape, but as the surface water flows, groundwater is often mimicking that movement underneath in the materials below our feet. So these are really important kind of baseline concepts that the general public often is unaware of or just maybe hasn't been exposed to. I still hear many times, even down in Kenosha area, I've heard people say how their well driller told them their well taps into the Lake Superior vein. So we still have a lot of work to do to help people understand the groundwater and the water cycle and how it impacts our lives. When we look at the watersheds, obviously those larger watersheds can be further subdivided. And this is an analogy or graphics that come from USGS, highlighting the difference between thinking of groundwater as a large bathtub If we put all of Wisconsin's groundwater in a large bathtub, or we brought all of the groundwater up to the surface, we would estimate that it covers the state to a depth of 100 feet. When we think of that, it's hard to comprehend how we might expect to find groundwater quantity or quality issues. If we're thinking of 100 feet of groundwater diluting out the different contaminants or chemicals, if we did a mass balance, we'd see that the impact is going to be much less than if we considered watersheds as kind of individual egg cartons, where if we have a certain amount of water in an egg carton and we're concentrating populations, we're concentrating land use within those individual watersheds, then it's much easier to identify where within the state or what communities are going to be impacted by quantity or quality. And then highlighting also that Wisconsin's climate is changing. So if we think of Wisconsin's water cycle, we get about 32 inches of precip each year. Of that, about 20 inches is going back to the atmosphere directly as evaporation or as uptake by plants. We estimate that about 10 inches of precip, annual precip each year, infiltrates, soaks down into the ground and becomes groundwater. So if our climate is changing and we're getting more extreme rainfall events or we're getting changes in temperature, these are going to impact our resource in different ways. And the Wisconsin Initiative on Climate Change Impacts does a great job of trying to model and help people understand what the impact of those changes is going to have on water resources. So that's setting the stage for helping us learn more about the groundwater resource itself. And our work is done because positions like mine exist because of the fact that groundwater is so valuable to our state. We looked at the base flow map, and Wisconsin is unique in terms of that connection to surface waters, but it's also unique in terms of our reliance on groundwater as our primary water supply. The communities along the Great Lakes obviously access Great Lakes water, but that's about 25% of the population that is relying on surface water systems. The rest of the communities, the rest of the municipalities, with the exception of some of the communities along Lake Winnebago, Lake Michigan, and Lake Superior, are relying on groundwater from municipal wells. And then obviously everyone that lives in the country or lives in rural areas has their own private well, which they're utilizing for their daily water needs. Almost all of the water for agricultural operations is coming from groundwater, 1/3 of industrial use, and 1/4 or 1/2 of commercial water use is groundwater. So the term buried treasure is a really apt name for this resource. And again, we are unique relative to other states in the United States in terms of how heavily we rely on groundwater. And as many of you probably are aware, there's a difference between public water systems and private wells. Public water systems are regularly tested. They have staff that are required to maintain the infrastructure. If any of the testing indicates issues, they're required to treat that water to ensure it's safe for distribution to their customers. Meanwhile, private wells, which are approximately 800,000 private wells scattered throughout the state of Wisconsin. You can install a private well essentially anywhere in the state and get enough water of good quality to be able to provide water for your family and the businesses or industries. These are wells that are not required to be regularly tested. There's some minimum testing requirements at the time of construction or when they may have to perform work or well replacement. But oftentimes there's large gaps between when a well is constructed and when somebody might need to replace a pump. 15, 20, even 25 years may go by before there's any sort of testing requirement, and those testing requirements were modified in 2014. So it's fairly recently that we've had this much testing going on for things like nitrate and arsenic. Prior to that, bacteria was the only thing that we had to consider for testing at a time of well construction. The other thing about private wells is the testing is great for educational purposes, but testing and finding a health-related contaminant does not require any sort of private well owner to take any corrective action. A lot of our programming that Extension does helps try to drive home the point that each well owner is their own water utility manager, whether they realize it or not. They're responsible for the day-to-day decisions about testing and any sort of additional measures that might result from the discovery of those results. But this also provides us an opportunity. So there's a gap in terms of oftentimes people's understanding of that responsibility of owning a private well, but it also offers an opportunity to engage the public in this idea of groundwater and their connection to the land and the water cycle. Private wells are a window into that resource. The fact that they're scattered pretty equally across the state gives us the unique ability to collect a lot of baseline data very efficiently with oftentimes willing partners. Everybody has a connection to that resource, and the vast majority of people have an interest in learning as much as possible. So for the past 50 years, Extension and the Center for Watershed Science at UW-Stevens Point, as well as a number of the partners here in the counties, UW-Eau Claire, I believe we've worked to input or gather data from UW-La Crosse, all of the data from DNR that goes into their system. We've helped to integrate into the Wisconsin Well Water Viewer, which helps paint the picture of water quality. What do we know about groundwater in the state of Wisconsin? And with nitrate, we have the most data out of any particular constituent that provides a really detailed look at where we're likely to find different concentrations or describe the different concentrations. What this resource does is if it has a minimum number of samples, it aggregates that data at different levels. So it might be a county, it might be a town range. It even gives you the ability to go down to a section, a 1 by 1 mile square grid cell, to see what information exists. So the cells that are color-coded mean that we've met the minimum threshold to aggregate that information. And then if we have an average concentration, the different colors correspond to nitrate levels, with the darker shades of red indicating higher concentrations of nitrate. And these maps exist for 18 different parameters. So things like chloride, total hardness, bacteria, atrazine-type pesticides. There's information that can be gained or learned from utilizing this online interactive tool. So what I'd like to do next is highlight some of the key parameters and talk about the red Cedar Watershed in particular in terms of what we know about water quality here in this watershed. When we talk about bacteria, bacteria is one of the most important things for private well owners to test for on a regular basis. The DNR well code, the DNR does regulate wells. They regulate well construction. And at the time a well is constructed, the goal is for that well to be able to provide a bacteria-free or sanitary water source. That's the one goal with well construction and a bacteria test. Annual bacteria test is one way to gauge, is that well capable of providing sanitary water, sanitary drinking water. When we look at bacteria, what we know statewide, approximately 15 to 25% of private wells, if we were to test them all at any one given time, we might expect that percentage to come back positive for coliform bacteria. Approximately 1% of wells also contain E. coli. E. coli is a much more serious situation because it confirms that either human and or animal waste may be contaminating that well water system. One thing you'll notice about this map is there's certain parts of the state that appear to be more prone to bacteria incidence than others. Bacteria in wells can be related to the well construction itself, but then there's also certain geologic considerations that we have to consider. When it comes to well defects, these are some pictures highlighting wells that tested or detected coliform bacteria. There's one of them that's labeled yes. That's a good looking well. The others labeled no highlight some pretty obvious problems of why that well was not capable of producing bacteria-free water. And there's very simple things that every landowner could do to inspect their system and maybe correct some of these things before they become an issue. So well construction, a lot of times may be a reason or the explanation for bacteria in a well, but then we also have to consider how the geology or what role the geology might play in some of the patterns that we see statewide. In karst topography, areas of shallow soils overlying carbonate rock are definitely going to make certain wells more prone to bacteria contamination. You'll see the cartoon or the animation on the lower right highlighting that not only is the geology in that picture a concern, but the well construction itself, the fact that that casing only extends to the top of the water table, might also present certain challenges. If there's a sinkhole, if there's rapid flow of water from the surface into the ground, it could contain bacteria, and there's oftentimes in that type of geology direct pathways for that water to enter a well. So deepening casing, well depth is important, but casing depth is equally as important a lot of times in determining whether or not a well is capable of producing the safest water possible. Casing, deepening that into the water table, it doesn't completely eliminate the chances of contamination, but it does mean that you're pulling water from much deeper, and the chances of direct pathways from the surface into that well are lessened or lowered as a result of a different or a modified well construction. Particularly in areas of karst potential, which is that map in the upper right, those are important considerations anytime somebody is drilling a well. And then you might also be wondering why the higher incidence in places like Taylor or Chippewa County. And there's areas of groundwater deficiency, areas where the glaciers did not leave behind a lot of sands and gravels, where it doesn't take a very long or deep drilling rig to hit that crystalline bedrock, which oftentimes is not only deficient in groundwater, but where you're relying on cracks or fractures to supply water to that well. And that geology, the limited geology or the limited groundwater in those areas seems to correlate with incidences of higher bacteria in those regions. So well construction is important. The soils and the geology are also important. And then there's certain land uses that also deserve special consideration. If we're talking about rapid infiltration of surface water, we have to be a little bit more careful about how we do things like applying manure or biosolids to those areas to prevent bacteria and other pathogens from entering groundwater and wells. Chloride is gaining increasing attention throughout the state. Chloride, we would expect natural levels to be less than 10 milligrams per liter. Chloride can come from fertilizers. Potash is generally in potassium chloride form. The plants utilize the potassium, but the chloride is highly mobile through the soils and oftentimes is responsible for some of the elevated levels that we might see in rural areas. Septic system effluent, particularly septic systems that are receiving or wells that require water softeners to treat that water, can discharge large amounts of chloride. But really it's road salt activities in the winter months, de-icing activities, that are responsible for some of the high concentrations that we oftentimes see. There's no health standard associated with chloride, but if it does get too high, there can be some aesthetic issues with corrosion. It can also give water a salty taste. If the source of that chloride is road salt, then there's a potential for higher levels of sodium as well. You'll notice the red Cedar Watershed is highlighted. The well water viewer is currently undergoing an upgrade. So by the end of the year, hopefully within the next couple months, there will be an integration of additional data. And the reason I highlight that is this will be the current map. So it's the same data, it's just a different color scheme, but you'll notice how much more data is filled in the Red Cedar watershed. And a large part of that is due to the work of places like Dunn County, Barron County, and others that have utilized the last couple of years to do some private well water programming or testing of their communities. With this next iteration, you'll see a dramatic increase in the coverage for a lot of these different parameters. The other thing I'll mention about chloride is we've worked with Wisconsin Saltwise to create a dashboard for chloride trends in public water systems. So public water systems don't test for chloride that frequently, but they do test for it. A lot of them do test for it frequently enough that we can start looking at how our chloride levels changing over time. And the gray dots are wells that are not changing with respect to chloride, but the blue are decreasing, and then the red ones or the pink ones are indicating wells increasing with respect to chloride. The size of that circle corresponds to the rate of change. There are a number of communities which we are seeing increases not only in chloride but potentially in sodium in those water systems. So chloride has not historically garnered a lot of attention, but as we test for it more frequently, as communities become more aware, we do expect to see this occur in other communities as well as they begin testing for it on a more routine basis. Arsenic is something that's naturally occurring. You'll notice that eastern Wisconsin, the communities along Lake Winnebago, the western shores of Lake Winnebago, are particularly prone to arsenic because of a specific geology. Some of the highest concentrations of arsenic anywhere in the world occur in Outagamie and Winnebago County. Fortunately, from a lot of that testing, they've been able to isolate what section of the aquifer it's coming from and recommend different casing requirements to try and avoid that from happening or occurring above health standards. In this part of the state, we still would recommend everyone test for arsenic at least once, but the data illustrate that arsenic is less of an issue in the Red Cedar watershed than it might be in some of the other parts of Wisconsin. Manganese is another naturally occurring contaminant or chemical. Wells that have issues with iron, if you have red or brown staining, that's associated with iron, but those wells would also have a higher potential for manganese. Manganese has less attention devoted to it over the last probably 20, 30 years. But recently, the Department of Health has instituted some health advisory language. So not only can manganese cause staining issues at low levels, but if it gets high enough, there's some health advisory potential for it related to Parkinson-like symptoms at levels above 0.3 milligrams per liter or 300 parts per billion. And you'll notice that northern Wisconsin, including parts of the Red Cedar watershed, are areas where we would expect to find elevated or higher incidences of manganese in people's drinking water. So this is something that people should be aware of and hopefully testing for on a more routine basis. Next, I want to get into some of the land use considerations and what we know about things like pesticides and nitrate in our water. Department of Ag, Trade, and Consumer Protection recently revised or updated a study that they perform approximately every 5 years. The previous one was 2017. The most recent one concluded last year and was published in this year, highlighting what we know about pesticide occurrence. So they select wells that are representative, spatially representative of the state of Wisconsin. They're looking for the percentage of agricultural activity and trying to get wells, the number of wells across the state that help represent those land covers across Wisconsin, specifically agriculture or cultivated land. And what that study shows is that 43.1% of private wells in this sample detected at least one pesticide. The most frequently detected pesticides were things like metolachlor, alachlor and its metabolites, atrazine and its metabolites, acetochlor, metribuzin, and clothianidin made the list this year. Clothianidin is a neonicotinoid, so anybody that's heard of neonics might know them in the context of their role in bee colony collapse or bee die-off. These are compounds that, when it comes to pesticides, are fairly recent. They haven't been used widely in the past, but their prominence, their integration into agricultural systems provides a sort of age dating technique to where if we're finding these compounds, it's indicative of fairly recent or young water. As we test for these more frequently, this particular study, the benefit again is that it's done every 5 years. By looking for these compounds, it gives us an ability to try and understand a little bit better how long it takes for some of this groundwater to reach wells or penetrate different parts of the aquifer. And the Red Cedar Watershed is kind of on this transition zone between more intensively cultivated areas in the forests of northern Wisconsin, and you're kind of right on that boundary to where we're seeing pesticides, and as you go north into areas of less cultivation, we see less occurrence of those chemicals in the private wells that were tested for this particular study. So pesticides are something that most homeowners, a lot of times it's out of the reach in terms of the breadth or extensiveness of the testing that DAGCAP does. That's testing that from a cost standpoint is out of the reach for most homeowners. Some of those capabilities don't exist at scale. So even if someone were interested, testing for some of these things is not going to be easy or maybe even possible. The other thing I'd mention about pesticides, I get a lot of calls from communities asking about Roundup, wanting to test for Roundup, or the chemical name for that is glyphosate. And this is not a commercial for Roundup. I'm not saying I'd want to drink Roundup. I'm not saying I'd want to apply Roundup. But when it comes to testing groundwater private wells for glyphosate, it's not a chemical that generally migrates through the soil very easily. DAGCAP does look for it. Even in their edge of field wells, very rarely, if ever, have they found it. That doesn't mean you wouldn't find it in surface waters as the result of runoff issues, but it binds to soil, it photodegrades. So if people are concerned about pesticides in their water, these are the tests. Metolachlor, alachlor are going to be the tests that are going to be most useful or have the most utility for helping people understanding the degree to which agricultural pesticide use is impacting their water. PFAS are emerging compounds. They burst onto the scene a couple years ago, and this has dominated the news over the last 3 to 4 years in particular. Our center worked with the Department of Natural Resources last year to conduct a statewide survey of PFAS in shallow groundwater. They were looking for specific characteristics. The well casing could not extend more than 40 feet into the water table. They were looking for sand and gravel, preferably sand and gravel aquifers where that was possible. And they divided the state into 450 grid cells with the goal of collecting 1 sample per grid cell. And they were successful in doing that. It's harder than it seems. When you look at some of the distribution of wells around the state, there were some particular areas where they had to work really hard to try and get a sample or pull a sample from an adjacent grid cell that would help them reach their goal of equally distributed across the state of Wisconsin. Some of the key take-home messages from that work, PFAS were detected in 71% of the shallow private wells that were sampled. Very few of them, I think there was only 4 out of the 450 that exceeded health-based guidelines. So the good news is that very few of the wells, less than 1%, actually exceeded health guidelines, but there were 71% of them that were detecting at least some level of PFAS, 1 or more low levels of various PFAS compounds, which I think they were looking at 30 to 35 different compounds in that study. They also did a whole host of other testing along with it to try and understand correlations of PFAS to more common contaminants. PFAS testing can be really expensive, so if we know of other compounds that might correlate to those compounds, it provides maybe some screening ability to help communities understand which areas or which wells to invest those testing capabilities on. They did notice that there was a correlation when we look at PFAS and its correlation to things like artificial sweeteners. Artificial sweeteners are a good indication of septic system influence or impacts. There was a strong correlation to PFAS with those sweeteners, indicating potential linkage to septic system drain field. So areas that had a higher percentage of developed land appeared to be more likely to contain low levels of PFAS compounds. Forested areas, not surprisingly, had the lowest overall detects of PFAS. The other thing that's important to note, that when we look at the highest concentrations of PFAS in that sampling, they were found adjacent to agricultural areas. Agricultural areas in general are not expected to contribute significant PFAS. But there are certain activities, things like spreading of municipal biosolids, maybe spreading of industrial sludges, that can influence PFAS concentrations. And again, some of the highest concentrations found adjacent to agricultural areas where it's likely that those type of activities were contributing to those really excessive or high levels. So there was a research paper published recently in an online journal that is open access, and the link is there. But anyone with questions about PFAS, helping illustrate that there's more and more information coming out every day that should help answer questions or maybe come up with better guidance for individuals on private wells or communities that might be looking for additional information on this topic. Just highlighting really quick the relationship of PFAS to densely developed areas. Not to pick on Linda in Chippewa County, but we've worked with Chippewa County very heavily in the past to try and understand linkages of land use to things like nitrate. And in that work, septic system density is something that we looked at or investigated. And this is an area or part of the state where they rely very heavily on small lot sizes, septic systems, and private wells. This may ring familiar for many of your communities as well, but this is what we mean when we talk about higher or more densely developed areas and risks for detectable or correlations to PFAS. Transitioning into nitrate. So nitrate is the most widespread groundwater contaminant in the state of Wisconsin. It moves very easily through soils. So not only does it have a health standard associated with it, which means that we have a lot of data on this particular element, but it moves very easily through the soil. So if nitrate's getting through, if there's elevated levels of nitrate being detected, it gives us an ability to help understand or predict what other types of compounds we might expect to find. It also helps us understand the degree to which land use might be influencing groundwater quality around the state. This particular element comes from fertilizers. It may come from manure or biosolid applications, septic system drain fields, even properly constructed drain fields we would expect to leach nitrate or nitrogen. There's also the health standard of 10 milligrams per liter because of concerns related to methemoglobinemia. That's a condition that, if left untreated in infants, can be fatal. There's also correlations to birth defects and miscarriages, not only in humans, but also in livestock as well. And then increasingly, there's more and more research to show correlations of things like nitrate to thyroid function or maybe various forms of cancer. So as a rule, we don't want infants or women who are pregnant or may become pregnant, we never want them drinking water with more than 10 milligrams per liter. And we'd encourage everyone to avoid long-term consumption of water with more than 10 milligrams per liter of nitrate nitrogen. There are treatment options available. The last year, the state of Wisconsin has relaxed or expanded some of the well compensation programs surrounding nitrate. It used to be that you needed, in order to qualify for well comp, you needed at least 40 milligrams per liter, and that well needed to serve livestock in order to access that funding. That essentially eliminated virtually most of the state of Wisconsin that's dealing with this from accessing that funding. Approximately 1 in 10 private well owners in the state of Wisconsin have nitrate above that 10 milligram per liter standard. There's less than, I think, 0.1% that exceed that 40 milligram per liter range. So the Evers administration decided to use some of the ARPA funding, the federal ARPA funding, to expand well comp with respect to nitrate, as well as things like bacteria, E. coli bacteria, arsenic, other parameters. But my understanding is that nitrate is the primary way in which people have qualified for that program. They devoted $10 million to it, and that $10 million is virtually gone. They're trying hard to utilize it, and they've been very successful at helping people access it. What that tells me is that there remains a need to assist those individuals that may be impacted by this, either with modifying or drilling a new well, or through some sort of treatment if drilling a new well is not going to be a good option, which in some cases, the degree to which we've penetrated the aquifer may mean that a new well is not going to solve or address somebody's issue. The map for the Red Cedar Watershed, I mentioned 1 in 10 exceed the nitrate standard statewide. Red Cedar Watershed is about 11%, utilizing the data that's currently in the viewer. So maybe right around the statewide average, but obviously not distributed equally across the watershed. So that's where a lot of the work that we're doing in these communities is helping to better pinpoint where we might expect to find nitrate in the state of Wisconsin or in particular communities. What makes this issue so challenging, why it's been studied and researched for at least the last 50 years, but we've made very little progress, is it's a widespread issue because not only are we concerned about it for health reasons, but the reason the nitrate's getting into our groundwater in the first place is it's generally acceptable, or even cases recommended practices that are contributing to nitrate getting into our groundwater. So we all know that a little bit of fertilizer is going to be good because it increases crop productivity. Above and beyond a certain point, it becomes excessive and we're going to leach large amounts to groundwater. But even at optimal rates, we have to be concerned about how much is getting into the system. The map, I shouldn't say the map, but the figure on the right is showing nitrogen recommendations for the different crops that we might expect to grow in the state of Wisconsin. So these are recommendations that come from UW Extension, the organization that I work for, showing that crops like potato and corn are requiring upwards of 150 to 200, in the case of potatoes,